In this lesson, we are going to have a look at transverse and longitudinal waves. Let's begin by having a look at this picture. In it, you can see a rather large water wave. You can gain a sense of how big it is by looking at the surfer on his surfboard about to be engulfed. I'm showing you this picture because water waves are the waves that most of you will be familiar with. You'll have seen them at the seaside. The picture, I think, conveys something rather important about waves, and that's that waves transfer energy, something we'll say more about later. This picture shows waves artificially produced. These again are water waves produced in a wave tank at the University of Edinburgh, and there's ongoing research into how we can get this energy from the waves and convert it into electricity, and that sort of work is ongoing. So you have seen an example then of a wave, a water wave. Let's have a look at what is going on inside a wave. So let's investigate what we mean by a transverse wave. Well, firstly, you need to be aware of what is meant by the medium. The medium of a wave is simply the substance that the wave travels through. So, for example, if we are considering water waves, as we are, then the medium is water. Okay, very straightforward. Right, look at the diagram shown. You can imagine we've got an x-axis and a y-axis there, and this represents a water wave which is moving to the right, and we're viewing it side on. Let's name some of its features. Well, you may already know that the top of the curved section of the wave is called a crest, and the lowest part is called a trough. The x-axis can be regarded as the position the water would be in if there were no wave present. So if it were completely calm water, then it would be flat, lying right along the x-axis. There would be no crests and no troughs. And that position is often called the line of calm or the line of zero disturbance. Now, the next feature of the wave we need to be aware of is the height of the wave, and that's called the amplitude. The amplitude is measured in meters, and it's a measure of the height of the wave measured from the line of zero disturbance right up to the top of a crest. You could also regard the amplitude as being the distance from the line of zero disturbance straight down to the bottom of a trough. They will always be the same in size. The next very important feature of a wave is called the wavelength. There is the wavelength shown there. Wavelength is given the symbol lambda. That's a Greek letter lambda. You'll need to get used to that. And the wavelength of a wave is simply the distance in meters between one crest and the next crest along. That's the adjacent crest. Simple as that. The distance between two adjacent crests is the wavelength. Now, I'd like to imagine a particle inside the water. One particle of water. There it is, the round circle there. If the wave is moving to the right, most people think that the water itself is moving to the right because the wave's moving to the right. It sort of seems plausible. But in fact, when you study waves carefully, what you discover is that the water particles themselves move in a different direction to what we see the wave moving in. In fact, the water particles go up as high as the top of the crest, and they then come back down, and they go as low as the trough, and then they repeat that motion over and over again. And that repeated to and fro movement is called an oscillation of the water particle. So we've got a strange situation in the transverse wave, whereby the wave itself is moving to the right, but the particles of the medium of the wave, the substance the wave is moving through, are oscillating up and down. So what is it that's actually moving to the right? Well, it's actually energy that's moving to the right. All waves transfer energy, and what we call the wave direction is actually the direction of energy transfer. So we can say the wave is moving to the right, that's the wave direction. We can say energy is moving to the right, but if we ever talk about the particles of the water, the particles of the medium, they oscillate up and down. And this is very important in a transverse wave. Note that the wave direction then, the direction of energy transfer, is always at right angles to the direction of the oscillation of the water particles. And this brings us to the definition of a transverse wave. In a transverse wave, like a water wave, the particles of the medium oscillate at right angles to the wave direction. And that's a definition that you should memorize. You should also remember that all waves transfer energy, not mass. It's not the mass of the water that's moving to the right, the water particles are moving up and down, it's energy that's being transferred. And a final note for you Latin lovers, the trans in transverse comes from the Latin for across, because the direction of the particles of the water move across or at right angles to the direction of energy transfer. The second type of wave you need to be familiar with is a longitudinal wave. So there are two types of wave that we study: transverse waves, which we've just talked about, and longitudinal waves. Now, in the lab, we do experiments with springs called slinky springs, where we can easily demonstrate longitudinal waves. And if you look at the diagram shows the coils of the slinky spring when a longitudinal wave is moving through it. Basically, big difference between a longitudinal wave and a transverse wave is that in a longitudinal wave, the particles of the medium, in this case the slinky, oscillate back and forth parallel to the wave direction. So if you look at that diagram, the wave direction is to the right, that's where the energy is going, and the particles of the spring, the coils, they are also moving right and then left, back and forth, right and left, parallel to the wave direction. So if we imagine a particle of the spring, one coil, shown by the red dot, how does it move? It moves left and right, just as shown. So that's a longitudinal wave. Sound waves are longitudinal waves, and in fact, sound waves are the only kind of longitudinal wave you will meet. Some vocabulary for longitudinal waves. The part of the wave where the spring particles are all squashed together or compressed is called a compression. So there's one compression shown. There's another compression, the next one along. And in a longitudinal wave, the distance in meters between the middle of one compression and the middle of the adjacent compression is the wavelength, and that's measured in meters as well. The part of the wave which is sort of stretched out is either called a decompression or in some textbooks a rarefaction. Okay, so that's basically a longitudinal wave. As I said, sound waves are longitudinal waves, and here's a graphic which helps you see what's actually going on in a real sound waves. The little black dots all represent air molecules, and in this scenario the sound is travelling from left to right. So if you can imagine someone shouting or a musical instrument, the sound is moving towards the right. Well, if you look at the dots, where the dots, that's the air molecules, are all squashed together or compressed, that's where they're more dense in the diagram. And where they're more spaced out, that's the decompression. If you look at the sort of wavy line above, Basically, that's a measure of the air pressure. So where the air molecules are all squashed together or compressed, you get slightly higher air pressure. And where they're more spread out, you get slightly lower pressure. And that pressure rises and falls, a bit like the slinky spring squashing and stretching. And that's the graphic which shows you a sound wave. This final diagram shows how you would produce a longitudinal wave and a transverse wave using a slinky spring. So if you look at the diagram, you would, to produce a transverse wave, you would lay the slinky on the floor. So we're viewing this from above. Grab one end of the spring and oscillate your hand from left to right as shown. Remember, we're viewing this from above, and the wave would travel to the right of the page, and you can see a wavelength there between two of the troughs. So in a transverse wave, remember then, the particles of the medium oscillate at right angles to the wave direction, and water waves are a good example of that. There's the oscillation. Remember, the medium is the substance the wave travels through, for example, water, or in this case, actually, the medium is the slinky spring itself. Here's a longitudinal wave. With a slinky spring, to do this, again, reviewing from above, you have to push your hand into the spring and then release it backwards. That's your oscillation back and forth. And as you can see, you get a compression and then a decompression, or sometimes called an expansion. And there's the wavelength between two compressions. So in a longitudinal wave, the particles of the medium oscillate parallel to the wave direction, and sound waves are an example of longitudinal waves.